Hello, my name is Abdurrahman Ahmed, and I am a PhD student at the University of Oslo at the Informatics Department. I am working together with my supervisors, Professor Jan Zeng and Professor Frank Gleason, trying to use machine learning for local energy flexibility. And I'm happy to share with you some of my recent work results. Of course, I would be happier if I could be with you physically. I will take these couple of minutes to present some of the results of a recently submitted paper in which we discussed using combinatorial auctions and graph neural networks for energy flexibility markets. My plan for this presentation is to start by giving a brief introduction about what is a combinatorial auction and what is the local energy flexibility market, and why we think combinatorial auctions are suitable for local flexibility markets. Then I will show our local combinatorial auction local flexibility market framework and its challenge, particularly the winner determination problem, which is a combinatorial optimization problem. And those challenge motivated our use for machine learning and graph neural networks. I will introduce how we represented those optimization problems in form of graphs, and how we used GNNS to imitate an expert solver to solve those problems. Then I end by showing some results and conclusions. Before I begin, I would say that I could not compress all the details in those slides. If something does not make sense to you, that means there is some missing. There is some piece of information missing. And I am more than happy, actually, to share small details if someone is interested. To start, I find it easier for me to understand combinatorial auctions when I think about their contrary, sequential auctions. And those are the ones we mostly think of when we talk about auctions. And the last week was my birthday, so I just came up with this simple example that I want to make a budget cake with 3 ingredients: flour and egg and sugar. And I decided to enter this weird auction that sells only those 3 ingredients. And of course, there is some other person or other people in the auction. Then I confidently submitted my bids for each ingredient. I just valued $1 for each ingredient. And the other person did the same, but she wanted only the flour, as she wants, I think, to make bread. And then the auctioneer determined the winners, and the auctioneer gives each item to the bidder who paid more. And now I personally do not really care how the other person now is so happy to make her bread, but I'm literally feeling exposed. And I cannot make my cake, and I cannot even use those 2 ingredients which I paid for. And this is what is called the exposure problem. And then I can start thinking at that moment that if I could combine I can combine some items in my bid, and emphasize the word combine here. And if I could combine the 3 ingredients together in a single bundle and just bid for 0 for any other combination of any ingredients, any bundle that does not contain the three ingredients together. So, and this exactly what is a combinatorial auction tries to help with. And it's kind of description of that is a market that in which participants can place bids on combinations of items, or can bundle or package different items together rather than individual items, and that of course they can make their birthday cakes. In fact, this bundling concept is very powerful and applied to many fields, particularly for the fields or the markets that where the items have some they're complementing each other, substitute each other. An example that could be the airport time slots, and of course it is not reasonable at all if the airlines company buys a time slot at the departure airport without ensuring that there is some time slot at the destination airport. So there's some kind of complementarity here. To see the similar picture in the energy markets, I just want to say a few words about the energy flexibility, and which has so many definitions in the literature, but all have in common is that it's kind of the ability of the power system to adapt to the sudden deviations in the supply and demand curve, and how to fulfill the need to compensate for that. This flexibility can be extracted from different parts in the power system, but my research, I am particularly focusing on the flexibilities that can be provided at the local vicinity, at the neighborhood level, at the prosumer side. Local flexible resources can be shiftable loads, can be rooftop solar systems, can be storage systems, and this local energy flexibility potential can be unlocked with the help of a newly proposed key player, that is the aggregator, which plays an important role to manage and gather all those low granular, small, scattered, flexible resources to contribute significantly at the system level. Basically, aggregators can provide different flexibility services to different parties, such as primary control to the transmission system operator, or balancing the balance responsible parties' portfolios. And my narrower focus is on the black part of this chart, is that I am concerned about the services that can be provided by the aggregator to the distribution system operators, the DSO, or the prosumers themselves. And I'm trying to use machine learning to propose some solutions for some foreseen problems. So now with that in mind, in this particular work, I'm trying to utilize combinatorial auctions for local energy flexibility market. You can think of or think about a case where the DSO is facing a sudden deviation in its supply and demand curve, and we need to compensate for that. We have mentioned that this flexibility can be extracted from prosumers' flexible resources through the aggregators, and prosumers can have many options. Prosumers with, for example, with PVs can provide energy to the system, pushing the supply curve up. Prosumers, for example, with batteries can do both, can either pushing the supply up by feeding the energy to the system, or by pushing the demand up, effectively decreasing the supply by charging the batteries from the grid. Electric vehicles and loads can do similar roles. The aggregator in the middle plays an important role, is to manage and gather all those low granular flexibilities to be significant to the DSO. At the end, a form of market a form of a market that we can call it local flexibility market is held to transact those flexibility services for some monetary values. To understand why combinatorial auctions are suitable for local flexibility markets, we assume, or we can think of, the DSO is facing some deviation and requesting this flexibility curve or flexibility request to compensate for the deviation. And you can see it as this: at time 12 and 13, 14, the DSO needs to increase the supply, or of course decrease the demand. At time 19 and 20, the DSO requests the opposite, which is decreasing the supply, or of course increasing the demand. On the prosumer side, we have four flexibility resources. The PV owners have their peak production, for example, the peak production at noon, at 12 noon, and one of the PV owners have a battery. The electric vehicle owner was planning to charge at time 14, and the washing machine owner is planning to wash clothes at time 17. Now, those prosumers can submit flexibility bids in different bundles. Now we have this DSO request, and we have these flexibilities can be provided by the prosumers. And now the prosumers from the left, that the PV owner can only bid for slot 12 because it just meets the noon and it doesn't have, he or she does not have a battery. But the PV with the storage prosumer can bid for any of these three slots, 12, 13, and 14, using the storage, emphasizing that those bids are mutually exclusive. So the EV owner can provide not to charge at time 14, as he or she was planning to, decreasing the total demand, and is going to decrease the total demand at that time. And the EV owner can also shift this demand to the time 14 to time 9, from time 14 to time 19, and bid for both time slots. The washing machine owner can do similar thing. The exposure problem does not appear explicitly here, but I think if both the PV and the PV with storage prosumers competed on time slot 12, this will decrease the total market efficiency. And as there will be some items could have been assigned but did not, and combinatorial auctions can increase the market, the energy market efficiency. So the temporal structure of the combinatorial auction local flexibility market can start with the DSO sending its flexibility need as a flexibility curve, requesting the market platform, and then which broadcasts this flexibility request to the aggregators, and then the aggregators together with their prosumers submit their bundles, their bundle bids. Then the market platform solves the winner determination problem and announces the winners. The most challenging bit in combinatorial auctions is solving the winner determination problem. I am showing the equations here, but what I want to say is that even if it looks like a straightforward linear optimization problem, the last integrality constraint pushes it to to the MP hard class of problems which have complexity that grows exponentially with the input size. Not that only, but what makes it more complicated to solve in our local flexibility market is that the correlation nature of between the valuation and the flexibility items, as well as the divisibility of the flexibility items that differentiates it from the usual commodity auctions in the combinatorial auctions literature. Yes, there are many algorithms to solve such problems. However, to choose algorithms, we should trade off between the quality of the solution and the computation cost. And we decided to take a totally different path, which is utilizing machine learning. Now our target is that if we can leverage this by incorporating machine learning, and there are different ways to incorporate machine learning, but in this work we aim to train an end-to-end machine learning model in a supervised approach. And our objective is to imitate an expert solver and to produce plausible, optimal solutions. And we based our models on graph neural networks. This is with a strong hypothesis that our local flexibility market winner determination problem instances, and because they belong to the same application domain, we hypothesize that they are sampled from an unknown probability distribution. And hence, we can use machine learning to lean a mapping between the problem instances and the solution. And hopefully that can generalize to instances that we did not use, or the model did not use during the training. To accomplish that, we followed 4 main steps. Because the first step, that because there is no gold standard allocation data set, we started with generating our problem instances. We use real-world PV production and generated prosumer bits. Then we used an expert solver, which is groupie, and to generate that to generate the solution to be our target labels. At the same time, we proposed a graph representation which encodes the local flexibility market and a determination problem in 3 types of nodes. The first is the bid nodes X in this figure, and where each node represents a bid, and we feature that by the bid price. The second type of nodes consists of the flexibility nodes beta, and represents the total capacity of each interval in the DSO flexibility request. The third type is the nodes of nodes is the mutual exclusive nodes. I call them alpha here, and to ensure that that each prosumer is just restricted to win at most 1 bid. And then adding edges will capture the relational structure between the nodes. Lastly, we design our graph network. I will keep the details of this for later discussion, or you may refer just to the paper. If there are 2 main results I would be happy if you take away from this, is that the first will be that the graph network models were able to output optimal solutions for the winner determination problems with less than 5% deviation from the expert solver based on the optimality value. So it's like on average on different number on a large number of solving instances. This, with the second takeaway, is that the model showed linear time complexity of the model's inference. Actually, inference time compared to the expert solver, and the expert solver has an exponential time complexity on the plots on the right side of this slide. The left side bars actually show how both the GNN model and the expert solver were able to fulfill the DSO flexibility need. This NRMST is a metric that we proposed, but we can just focus on how close the blue bars from the orange bars in each winner determination problem case, which tells how the GNNs were able to imitate the expert solver in fulfilling the DSO request. If I may conclude this presentation, I would say that we propose a combinatorial auction framework for local energy flexibility markets, and we developed a tripartite graph representation to capture the dependencies of the winner determination problem to be naturally consumed and processed by the graph neural network model. And the average deviation on the optimal value is below 5%. The model showed linear time complexity of the model's inference compared to the expert solver, exponential complexity, and this may be the best selling point of using machine learning for this particular point, particular problem. And we also compared how the models fulfill the flexibility need of the DSO compared to the expert solver. The model's deviation average is below 7%. That's what I have, and thank you very much.